Okay, so let's continue our discussion. So we built up this model for spring mass system last section. Okay, now we said 2 lambda is actually beta over m. Beta is the damping coefficient, m is the mass, and k is the spring constant from Hooke's law. M is the mass, so w square is k over m. Now within this model there are several cases. Now let's say you do not have a forcing term, or actually a driving force. So driving force is modeled by g, a function of time. Then the driving force is 0, means g is 0. Okay, no driving force. Then all of a sudden what you get is actually a homogeneous second order differential equation. And it's linear, right? 2 lambda and w square are constants. Okay, so we call this a free response. So we use the word free because there's no driving force. Okay, so whenever you see free motion, that's no driving force, so keep that in your mind. Okay, now again we go on furthermore and say, let's assume there's no damping in the system. Okay, there's no frictional forces. Well, it's sort of unrealistic, but let's assume. So what is the part of the equation that takes damping into account? Well, lambda is, right? So if lambda is 0, then this differential equation can be rewritten in this simple manner, because lambda 0 means that dx over dt term is going to vanish, right? So we get a simpler differential equation. This is the situation where there's no driving force and where there's no damping, and this differential equation to model the situation. And now think, we call it a simple harmonic motion or free undamped motion. Now what is the motion will look like? It has an interesting behavior. Now think about this situation physically and think what is the eventual motion is going to be look like. Okay, you let the mass oscillate, and after long time, is it going to get stop? Is the motion going to stop? No, right? Because you don't have any damping. Energy does not drain out. There's no frictional forces, right? So the motion will go on forever with a certain pattern. Now, what do I mean by a pattern? Let me show you a nice cool picture. So this is how the motion is going to run. See? So you have the motion here, the mass here. It's going to get up, oscillate, down, and similar shape, down, and similar shape, go on and on forever. Okay, I'm not the best artist, so these parts should be similar to these parts. Okay, so we call this a periodic motion, right? Okay, because we have a period. Let's take a one section, well, a one cycle. So let's say this is a one cycle. This part, you can see this motion, this up goes down and up, it keeps repeating, right? Okay, well, I should go on, the period should be defined, let's say, or this is a period, let's call it for simple. So you can see you have the same motion over and over on. Okay, so it's periodic. The motion is keep repeating the shape of this motion. Okay, so that is why we call a periodic motion. What does this remind you? What type of a graph is this? Where do you see, for what type of functions you see this type of motion? Sine and cosine, right? Now what is the connection between sine and cosine? We will see in a few seconds. Okay, let's go to our differential equation model. Right, now we know now the motion is going to go forever. Okay, that's the application. Now how do we solve this model? What is the method you use? Well, this is a homogeneous second order differential equation, so you can use the auxiliary equation method, right? So when we use the auxiliary equation method, okay, the auxiliary equation we get is, well, now pause the video and try to come up with the auxiliary equation by yourself. Okay, we have done this in section 4.3. So it's going to be m square plus w square is equal to 0, because we assume x to be, x is the dependent variable, e to the mt. Okay, Usually we assume this to be y is equal to e to the mx, but now y is x, or the dependent variable is x is t, right? So don't get confused. Try to do it by yourself, okay? All right. So this is the auxiliary equation. Well, now we have to find the roots. So what type of roots you have? Again, pause and try to think what are the roots. Well, the roots are complex roots, plus or minus wi. This is something you should be able to derive by now. So that means alpha is 0, beta is w. So our solution should ideally look like x is equal to e to the alpha t, 0t, e to the 0 is 1. So C1 cosine beta, beta is w, cosine wt plus C2 sine wt. Alright, now the solution for the differential equation look like this. O motion at time t, so x is the displacement at time t. The displacement after time t is actually a superposition, you can see, summation of a sine and cosine function. So it does make sense, right? Why we had that nice looking sine and cosine type of a motion. Well, the reason is the solution is in fact created out of trigonometric functions. Okay, so when time goes on, the motion look like this trigonometric type function, which is periodic. Okay, all right. So then we have to learn couple of notations, or the terminologies, ideas, whatever you call them. Period. So a period is, you saw that you have a cycle, you know, you have a path that keep repeating. That is a periodic motion. So something like this, or something that you decide to take like this. This shape will keep repeating on and on. So this we called a cycle. The time that it takes to complete this type of a one cycle motion is called a period, which is given by time. It's a time, okay? It's the time that it takes one cycle to complete, 2 pi over w. W, you know, w square is k over m. So you have to keep remember that, okay? Frequency is actually how many cycles that you complete within a 1 second. So it's 1 over time that it takes for a period, right? Or the period. So frequency is 1 over time. And amplitude, okay, amplitude is actually the height of this motion. Okay, so that is the amplitude. One positive height or the negative height, the height of this motion. Okay, all right. So then, well, we are going to use a magic trick. So we know the solution look like C1 and C2 are two arbitrary constant. We said the motion is C1 cosine plus C2 sine. We can use trigonometric identities, which you are not going to do in this course, okay? And we do not expect you to write this solution in the simpler version, but we can use the simpler version, okay? And we can, instead of writing your solution as a summation of cosine and sine, we can write it as just as a cosine function, which is a cosine wt minus phi. Phi we call the phase angle, or we can write it as a sine wt plus psi. Okay, if we use some trigonometric identities, which is complicated and time consuming, and we don't expect you to do it. Okay, but actually this a is the amplitude. Okay, but it has a connection with how to find amplitude. So it turns out amplitude is actually c1 square plus c2 square root. Okay, square root of c1 square plus c2 square. So whenever you get the solution, okay, don't worry about this trigonometric simplification. When you get the solution, you get two arbitrary constants, c1 and c2. So if you are asked to find the amplitude is now square those constant, add them and take the square root, and that is your amplitude. That is the only thing that you need to know, okay? Not the conversion of this trigonometric conversion, okay? But that is useful. That trigonometric conversion is usual if we want to graph it by hand, okay? But that's not something again that we do, okay? Just know how to find the amplitude. I will do an example in the next video, okay? So this is free undamped motion. Let's see an example in the next video then. Thank you.